We often remember the Battle of the Atlantic in terms of U-boats and torpedo wakes, a clear, visible fight between steel titans on the surface. But history suggests the true threat, the one that paralyzed British ports and threatened to starve an entire nation into submission in the winter of 1939, was something far more insidious. It was a weapon you couldn't see, couldn't hear, and certainly couldn't shoot back at. This is the story of the myth of detection versus the reality of the phantom mind. Many of us remember the newsreels from the early days of World War II, the Blitz, the dogfights over the Channel. Yet, tucked away in the Admiralty reports, there was a far more chilling reality. In late 1939, ships, cargo haulers vital to Britain's survival, and even naval destroyers began simply vanishing. They didn't sink slowly. They were often obliterated from beneath in a single, massive detonation that left little trace but a widening ripple and floating wreckage. Initially, the High Command was baffled. Their best minesweepers, designed to snag contact mines with large paravanes, sailed right over the danger zones and came back clean. But the ships kept dying. The ports of Britain, the beating heart of its entire supply chain, were quickly becoming death traps. Think of it this way. You've prepared for a visible opponent, a boxing match where you can see the punch coming. But the Germans, with cunning, decided not to attack the ship directly. Instead, they attacked the laws of physics that govern the ship. They had weaponized the simplest feature of every vessel we built: steel. When a steel hull is built, hammered, welded, and left to sit in the Earth's magnetic field, it takes on its own magnetic personality. It becomes effectively a giant, slow-moving bar magnet. This magnetic field wasn't seen as a vulnerability, yet it was the perfect Achilles heel. Every time a ship sailed, it was sending out a silent, invisible signal to the mines waiting below. The German weapon, known as the Luftmine B, LMB, was elegance in its simplicity. It lay on the seafloor, patiently waiting. Inside its casing, a finely tuned magnetic sensor, a needle, or later a flux meter, registered the change in the Earth's natural magnetic field caused by the passing of that huge steel hull. That change, measured in units called Gauss, was the trigger. The mine was set to explode with a minimal magnetic change, a change so small it's nearly imperceptible, yet massive enough to obliterate a merchantman. The results were immediate and horrifying. The ship was broken cleanly in two, a technique that ensured minimal survivability and maximum confusion. The stakes were clear. If the convoys couldn't dock, if the ports couldn't be cleared, Britain would be isolated. Food, oil, ammunition, and raw materials would cease to flow. This wasn't just a military crisis, it was an existential one. They had to know how this thing worked. They had to understand the invisible law the Axis had belittled them with. They needed a sample, an unexploded mine, and they needed it immediately. The lives of thousands of sailors and the fate of the war itself depended on a single moment of scientific discovery. The game had shifted from brute force naval combat to a subtle, desperate contest of physics. If the introduction established the crisis, the vanishing ships, this chapter reveals the terrifying hidden mechanism that drove it. To understand the Axis weapon, you have to understand a concept that seems counterintuitive, that every steel ship is already a weapon aimed right back at itself. Think about your own ship. Whether it was a destroyer, a freighter, or a fishing trawler, it was constructed in a shipyard, likely over months or years. Tons of steel plates were cut, bent, and riveted or welded together. Now consider where that steel was during this process, sitting right in the middle of a massive invisible force field, the Earth's own magnetic field. When a piece of steel is hammered, heated and held in place while the Earth's field runs through it, that steel becomes magnetized. It's the same basic principle as creating a permanent magnet by rubbing it against another magnet. Except here, the Earth itself, acting as a giant magnetic dipole, is doing the rubbing. The effect is not uniform. The ship's structure, due to its orientation on the slipway, north-south versus east-west, and the intensity of the hammering, acquires what we call permanent magnetism. Imagine a bar magnet thrust right through the keel of the ship. It has its own north pole and south pole, fixed and unwavering, traveling with the vessel wherever it goes. But there's a second, more complicated layer, induced magnetism. When a steel object is placed in an external magnetic field, it temporarily enhances that field. So when your ship sails into the North Sea, the steel hull concentrates the Earth's field, amplifying it right beneath the ship. Change the ship's heading, and the pattern of induced magnetism changes immediately.
The Axis High Command wasn't interested in the vast magnetic field of the Earth. They were interested in the anomaly, the small, sudden disruption caused by a ship passing overhead. The German mine scientists were genius in their simplicity. They knew a steel hull, even one a few hundred yards away, would cause a distinct bulge or depression in the Earth's magnetic field lines directly below it. This led to the design of the Luftmine B, or LMB, dropped often by aircraft, which helped keep the enemy weapon shrouded in secrecy for months. The mine didn't need to touch the ship, it just needed to sense the ship's magnetic ghost. The heart of the mine was its trigger, set to measure the change in the vertical component of the magnetic field, the up and down pull. Why the vertical component? Because as the ship passed, the main distortion of the field lines was compressed or stretched vertically, making it the most reliable trigger point. They quantified this trigger with incredible precision, using a unit familiar to physics students, the Gauss. Early German mines were set to detonate with a magnetic change of only about 15 milligauss. Now, to put 15 milligauss in perspective, the Earth's total magnetic field strength at the latitude of Britain is around 500 milligauss. The amount of change required to trigger the mine was only about 3% of the ambient field. It was the equivalent of requiring a car driving down a highway to detect the subtle, sudden shift in gravity caused by a small suitcase dropped 50 feet away. It was exquisitely sensitive, and that sensitivity made conventional minesweeping useless. The mine's sophistication didn't end with its hair trigger sensitivity. It was designed to exploit the very nature of a ship's movement. The proximity fuse. The mine was typically dropped in shallow coastal waters or harbor entrances. As a ship passed directly over it, the magnetic field reached its peak intensity, triggering the fuse. The massive charge. Inside the casing lay a massive 450 kilograms, nearly 1,000 pounds of high explosive. The effect of pressure. Because the mine detonated under the ship, often beneath the keel or in the bilge area, the explosion didn't just smash the hull, it used the water itself as a deadly intermediary. The explosion created a massive momentary bubble of high-pressure steam and gas. This bubble was forced violently upwards against the hull. The sheer pressure wave hitting the ship's weakest point was enough to snap the keel of large vessels or lift smaller ships entirely out of the water, breaking their backs before they even landed again. That's why the damage was so catastrophic and why survivors were so rare. The ship was simply broken in one clean, brutal motion. The Axis attitude was clear from the start. We have created a perfect weapon that renders your entire fleet vulnerable, and you lack the intellectual means to understand or counter it. They were betting on the Allies clinging to old methods of detection, dragging lines and sounding devices, while the true killer sat motionless, communicating only in the silent language of physics. Therefore, the problem wasn't tactical, it was scientific. The Allies didn't need a stronger boom or a tougher hull. They needed to find a way to silence the ship's magnetic signature. But before they could silence it, they first needed to capture and dissect the device itself. That terrifying necessity, the need to retrieve an unexploded phantom, is what set the stage for the scientific breakthrough that saved the war at sea. The entire Allied war effort, the flow of blood life across the Atlantic, hinged on one grim necessity. They needed an unexploded German magnetic mine intact. It was the ultimate contradiction. The only way to disarm the enemy's phantom weapon was to physically confront it, hoping it wouldn't choose that exact moment to detonate. Desperation reigned in late 1939. Merchant ships continued to vanish with unsettling speed, yet the British were still flying blind. Their scientists could theorize, but without a concrete sample, every countermeasure was a wild, costly guess. Then, fate, or perhaps just the changing tide, intervened. On November 23, 1939, near the small coastal artillery testing range at Shoeburyness in the Tom's Estuary, a German mine was spotted. It hadn't fallen into deep water where the proximity fuse could kill. Instead, dropped perhaps a moment too soon by a German aircraft, it had landed in the shallow mudflats and become stranded at low tide. The moment that weapon was spotted, lying exposed, the twin horns and the parachutes still attached, was the moment the tide of the Battle of the Atlantic began to turn. It was a priceless, terrifying piece of intelligence, but getting to it meant risking instant annihilation. Therefore, the recovery mission wasn't a standard military operation. It was a high-wire act of scientific and physical courage. The team dispatched to Shoeburyness was a mix of naval ordnance experts and civilian scientists led by two brave lieutenants, John G. Avery and Roger Lewis. Their instructions were clear, born from the terrifying understanding that any ferrous metal could trigger the mine.
The protocol they devised was radical and extraordinary. Before approaching the mine, every man had to be stripped of all magnetic material. This meant taking off their uniforms and wearing special, non-magnetic overalls. They removed all buttons, belt buckles, wristwatches, and even metal dental fillings were a source of discussion. It was a literal stripping down of everything man-made, ensuring they brought only their minds and their courage to the task. The tools used were equally critical. To avoid disturbing the highly sensitive magnetic field, they couldn't use standard steel wrenches or probes. Instead, they relied entirely on non-magnetic brass tools, custom-made shovels, wrenches, and hooks. As they worked on the exposed mud, the race was against the clock. They knew the mine had an inherent fail-safe, a hydrostatically operated clockwork mechanism that would eventually arm the magnetic sensor, often after a 30-second delay upon hitting the water. If the tide came in even a little, the mine would effectively rearm, turning a controlled dissection into a deadly gamble. Lieutenant Avery, acting with immense calmness, managed to expose the mine's fuse pocket, carefully unscrew the fuse with the brass tools, and carry the entire heavy assembly, the heart of the Axis weapon, back to the shore. It was an act of profound bravery that immediately unlocked the secrets of naval survival. The recovered mine was immediately rushed to the Mines and Torpedoes establishment at Portsmouth. The scientists, working behind guarded doors, finally saw the mechanism that had claimed hundreds of lives. What they found inside was not a clockwork masterpiece of complexity, but a brilliantly simple piece of electrical engineering, a mechanism designed to detect a change in the vertical magnetic flux. It confirmed the theory. The ship was the trigger. The most critical figure in decoding this captured device was a Canadian scientist working with the Royal Navy, Commander Charles F. Goodeve. Goodeve, a physical chemist by trade, was the intellectual architect of the solution. Analyzing the sensor's sensitivity, which measured the magnetic change in Gauss units as established by the German scientists,
Goodeve realized the solution was to create a specific counterfield. He coined the term for the process, de-Gaussing. The logic was simple, yet took a genius to apply. If the steel hull carried a permanent magnetic signature that triggered the mine, and if the ship also induced a temporary magnetic field from the Earth's field, then the solution was to create a third, engineered magnetic field that would perfectly cancel out the first two. It was like setting up a soundproof room. To block the sound from the outside, you don't just build a thick wall. You use an opposing frequency to cancel out the incoming waves. Here they needed to generate an opposing magnetic field that made the huge steel hull appear to the mine below as if it weren't even there. This intellectual pivot from trying to detect the enemy mine to trying to cloak the friendly ship was the essence of the scientific breakthrough. The Germans' hubris, relying on their superior weapon to remain unknown, had been defeated by a stranded mine and the bravery of two officers on a muddy beach. Therefore, the recovery at Shoeburyness wasn't just a win, it was the entire foundation for the defensive war at sea. It provided the precise blueprint for the coil systems and wiping procedures that would save the convoys, leading directly to the immense logistical challenge of arming the entire fleet with the electromagnetic shield that Commander Goodeve had just devised. With the secret of the German mine now unlocked, the problem shifted dramatically. The war became an engineering and logistical race. The intellectual breakthrough of Commander Goodeve, that they could cancel the ship's magnetism with an opposing magnetic field, had to be scaled from a blackboard theory to a fleet-wide defense, and it had to happen virtually overnight. This led to the deployment of two primary countermeasures: the immediate high-volume temporary solution known as deperming or wiping, and the intricate permanent solution known as coiling.
When the early magnetic mine crisis struck, the sheer volume of merchant vessels and naval ships requiring protection was staggering. There was no time to install complex electrical systems into thousands of ships simultaneously. Therefore, the first widespread countermeasure was a brute force approach that solved the immediate problem: deperming, often called flashing by the sailors. Think of deperming as a giant magnetic reset button for the ship. The process involved putting the ship into a large, often shore-based system of huge electrical cables laid on the seabed or strung around the vessel in a dry dock. The ship would be carefully positioned, and then a colossal, controlled pulse of direct current was sent through these external cables. In other cases, for ships already at sea, a massive current-carrying cable, sometimes pulsed with up to 2,000 amps, was physically dragged up and down the length of the hull, often while the ship was underway. This temporary, powerful magnetic field scrambled the ship's existing permanent magnetism. It didn't eliminate the magnetic signature completely, but it temporarily reduced it to a level that fell below the 15 milligauss sensitivity threshold of the early German mines. The effectiveness of this rushed solution was proven during the crucible of the Dunkirk evacuation in May 1940. With the entire British expeditionary force trapped, every available vessel, from Navy destroyers to civilian pleasure craft, was suddenly needed. The waters approaching the French coast, however, were infested with German mines. Therefore, in a frantic, monumental logistical marathon, the British worked round the clock, often using the deperming technique, to temporarily protect the fleet. Historians credit the Navy with managing to wipe or de-gauss over 400 ships in the 4 days leading up to the main evacuation. This effort, often overlooked in the stories of the little ships, gave those civilian vessels the essential momentary immunity they needed to pass through the magnetic minefields and bring the troops home. It was a victory of sheer willpower and quickly applied science. While wiping was an essential stopgap measure, it was temporary. A steel ship would slowly reacquire its magnetic signature through exposure to the Earth's field and the constant pounding of the waves. For the essential long-term security of the Navy and the critical merchant convoys, a permanent internal solution was required: coiling. The concept was brilliant. Install the opposing magnetic field inside the ship. This was accomplished by running thick copper electrical cables, the M-coil, or main coil, horizontally around the entire circumference of the hull, usually just below the main deck. The current running through this coil was carefully calibrated to create a precise magnetic field that flowed in the opposite direction of the ship's strongest permanent vertical magnetization. The two fields effectively canceled each other out, making the ship nearly magnetically neutral to the mine sitting on the seabed. The installation was incredibly complex and time-consuming. It involved measurement. The ship first had to pass over a De-Gaussing range, a network of sensitive magnetic sensors laid on the seabed to measure its precise, unique magnetic signature. Calibration. Electrical engineers then calculated the exact current in amps and the number of cable turns needed for the M-coil. Installation and monitoring. The cables were painstakingly installed. Crucially, the system required constant management. Sailors, often specialized electricians' mates, had to monitor the current flows and gauges, continuously working in 3-watch shifts or 24-hour shifts to ensure the system was functioning. This was a new, unsung duty of naval warfare. The complexity did not end at installation. Commander Goodeve's team realized that the induced magnetism, the temporary field caused by the Earth, was the real variable, and it changed dramatically with latitude. Think of the Earth's field lines. Near the equator, the field lines are almost horizontal. Near the poles, they plunge almost vertically into the ground. A ship sailing from Britain down to South Africa was moving across entirely different magnetic environments.
Therefore, the M-coil system was designed to be reversible. As the ship crossed the equator, where the Earth's field flips its vertical direction, the crew had to reverse the polarity of the current in the M-coil. If they forgot or failed to do this, the Degaussing coil, instead of canceling the ship's magnetic signature, would suddenly double it, turning the protective measure into a deadly beacon for any mine in the southern hemisphere. This detail highlights the extreme mental and technical vigilance required for Allied sailors. The scale of this logistical task was immense. The Admiralty estimated that they would need to coil around 2,400 vessels, from warships to critical merchantmen. The industrial effort required to build the cables, manufacture the power supplies, and install and maintain these systems across global shipyards was a silent, sprawling war effort in its own right. A war won not with shells, but with ohms and amperes. Therefore, the solution to the German magnetic mine was not a singular invention, but a massive, layered infrastructure built on the bedrock of pure physics. It was the successful application of the scientific method under wartime pressure, turning a moment of crippling vulnerability into a sustained quiet advantage that fundamentally protected the lifeblood of the Allies. The implementation of degaussing, the swift, widespread coiling and wiping of the Allied fleet, achieved its primary goal. It brought the devastating immediate sinkings of 1939 to a screeching halt. But in warfare, a successful defense only guarantees one thing: the enemy will adapt. The Axis High Command, faced with the fact that their magnetic superweapon had been neutered by a counterfield, immediately began work on a counterpunch. The silent war below the waves transformed from a challenge of detection into a brutal, unending competition in fuse technology. The Germans quickly realized that the Allies had cracked the code for their simple magnetic field. The response was the development of mines that were no longer satisfied with a single magnetic signature. They introduced two devastating new elements that made sweeping and countermeasures far more complicated: ship counters and multi-effect fuses. Think of the early mine as a simple magnetic tripwire. The new mine was a sophisticated electronic gatekeeper. The new mine series used an inertia fuse and a pressure fuse in addition to the magnetic sensor. Now, a ship needed to cancel not just its magnetic field, but also account for the shock wave created by its propellers and the pressure displacement of its hull, all simultaneously. A vessel could pass over a mine with a perfect magnetic cancellation, only to be detonated by the massive pressure wave it created. But the most insidious development was the introduction of ship counters. The Germans reasoned that if the Allies were attempting to clear harbors by dragging non-magnetic sweepers, they would simply teach the mines to ignore them. These new fuses were electronic marvels, capable of detecting the change in the magnetic field, but deliberately not detonating until the 5th, 7th, or 10th vessel passed overhead. Therefore, the psychological warfare was terrifyingly effective. A minesweeper could pass safely, leading the captain to declare the channel clear. But the next ship, a valuable merchantman laden with vital cargo, would be the one to pay the ultimate price. This forced the Allies to sweep channels 10 or even 20 times before they could be considered truly safe, grinding the logistical pipeline down to a crawl. The Axis had succeeded in using paranoia as a weapon. Even when sticking purely to the magnetic principle, the Germans continuously improved the sensitivity of their fuses. As the Allies became adept at tuning their degaussing coils to achieve a near-zero magnetic signature, the Germans simply lowered the required threshold for detonation. While the early mines required a 15 milligauss change, later improved models could be triggered by a shift of just 4 milligauss. The truth of degaussing is that it was a never-ending job, an essential but costly routine that separated the surviving ships from the losses. While the M-coil was the permanent solution, the magnetism it countered, the ship's permanent signature, was constantly being altered. Think of it like tuning a radio. You find the perfect spot, but as you drive, the signal drifts. A ship's magnetic signature was never static. It was always in flux due to mechanical stress. Heavy seas, enemy fire, or even hard docking maneuvers could physically realign the steel molecules in the hull, instantly creating new magnetic hotspots.
Latitude change. As noted earlier, the ship's position on the globe constantly changed the Earth's magnetic influence, requiring crews to diligently adjust or reverse the coil polarity. Induced magnetism. The simple act of sailing in a constant direction for days would induce new magnetism that needed to be periodically canceled out. Therefore, every naval base, every major port, became home to the Degaussing range. These were specialized shore stations where vessels would pass over a series of magnetic sensors laid on the seabed. The ship's exact signature would be read by engineers on shore, allowing them to calculate the necessary adjustments to the coil currents. This was mandatory maintenance, a quiet, routine inspection that held the key to the ship's survival. Furthermore, captains were often instructed to change direction as often as possible when on the open ocean. This simple, tactical measure was designed to prevent the buildup of induced magnetism from the Earth's field, forcing the ship to constantly re-randomize its temporary magnetic signature and make it harder for a mine to lock on to a consistent pattern. The war against the magnetic mine was not a singular victory. It was a testament to persistent scientific vigilance. The Axis had launched a challenge based on physics, and the Allies responded with continuous adaptive engineering. The Degaussing grid did not eliminate the mine threat, but it gave the Allies the intellectual and logistical superiority needed to keep the shipping lanes open, a silent, grinding victory that ultimately secured the supply lines necessary for victory in Europe. We conclude where the war below the waves truly found its balance, not with a dramatic naval battle, but with the quiet, persistent victory of science. The trusted grid, the coils, the cables, and the routine maintenance ultimately secured the lifelines of the Atlantic. The Degaussing program wasn't the kind of heroic victory that earned headlines, but it was the kind of indispensable effort that won the war. The true measure of this technological triumph lies in the statistics that never materialized. The Degaussing program didn't win a specific battle, but it prevented thousands of ships from becoming victims. While the exact final count of ships saved is impossible to tally, historians widely agree that the technology gave the merchant marine a twofold increase in safety against the magnetic mine threat. That quiet efficiency, multiplied across 4 years of conflict and thousands of transatlantic voyages, saved not just ships, but untold thousands of lives and millions of tons of vital supplies. Many might assume that degaussing is a relic of World War II, a clever trick shelved after VE Day. But the silent intellectual war against magnetic detection never ended. Today, decades later, the principle devised by Commander Goodeve is still a fundamental aspect of naval warfare. Modern warships, particularly those operating in coastal areas, are still protected by advanced versions of the M-coil. They are constantly monitored and degaussed because the threat of sophisticated magnetic proximity mines remains acute. It is a necessary admission that the laws of physics, once weaponized, must be countered with continuous scientific vigilance. Furthermore, this 80-year-old technique found a second, unexpected life in the digital world. The very principle of using an opposing electromagnetic field to neutralize a permanent magnetic signature is the basis for degaussing machines used today to securely erase data. If you need to permanently and irreversibly destroy information on an old hard drive or magnetic tape, you run it through a powerful degausser. The technology that saved the Allied convoys by scrambling magnetic fields is the same one that safeguards modern sensitive data by scrambling digital fields. The story of the magnetic mine and degaussing is ultimately a tribute to the overlooked heroes of the war, the engineers, the scientists, and the electricians' mates who maintained those coils day and night. They didn't fire guns or pilot planes. They wrestled with amperes and Gauss, translating high-level physics into practical, reliable survival equipment. Therefore, the legacy of the trusted grid is a profound one. It proved that the intellectual flexibility to solve a problem based on first principles, to ask why the ships were sinking, not just what was sinking them, is often the decisive factor in any conflict. It was a triumph achieved not through explosive force, but through quiet, methodical science, ensuring that the supply lines and the faith of a nation remained unbroken. Thank you for joining us on this journey and for helping us keep these vital stories alive. Stay with us to keep learning.